Okay, this is a quick tank mixing problem. We have a tank that we're going to suppose holds 100 gallons or up to 100 gallons. It currently has 50 gallons of water in it with 2 pounds of salt in it. Brine solution is pumped in at a certain rate. Well-stirred mixture leaves at a certain rate. We're going to write and solve an initial value problem. A of t is the amount of salt in the tank at any particular time. The differential equation that models the situation is the mix coming in times the rate it comes in minus the mix leaving times the rate out. So the mix coming in is 3/2, and the mix leaving, so that's the mix coming in. The mix leaving is the amount of salt at a particular time divided by the volume, and that's true all the time. So for any of these problems, we need to figure out the volume. So let's figure out the volume. Volume at time t is what is currently in there plus the rate at which it enters, and it enters at a rate of 4 pounds a gallon, and then minus the rate at which it leaves. So we're going to enter 4 gallons per minute minus what leaves at 2 gallons per minute. And so our volume at any particular time is 50 plus 2t. The tank is filling up. So let's mention that. Tank is filling up. And then the question is at what time will the tank be full? If it holds 100 gallons, it already has 50, and it's filling up at 2 gallons per minute, then we would have 100 gallons equals 50 plus 2t. If we solve this, it'll tell us what time the tank is full, and that would be when t is 25 minutes, the tank will be full. So t 25 minutes, tank is full. That volume also imposes a domain on the problem. So for a domain for the problem would be 0 to 25. That's what makes sense, is a domain for a of t, which we're going to find when we solve this. So going back to a prime of t, we need our mix rate n. Let's write that out. We have a prime of t is equal to mix coming in is 3/2 times the rate at which it enters, which is 4. So times 4 minus the mix leaving, that was a of t divided by the volume. Volume was 50 plus 2t. 50 plus 2t times the rate leaving, and the rate leaving was 2 gallons per minute. So times 2. There is your equation. You could simplify that if you want, but I won't yet. I'll just leave the equation like that. We also need our initial condition, which is the amount of salt at the start time, which is time 0, and it was 2 pounds of salt were dissolved in the tank. So a of 0 is 2. When it comes to writing an initial value problem, here is our initial value problem. Okay, I'm going to pause for a second and get a new screen, and then we're going to solve that differential equation. Okay, we're back. We're moving on to solving that differential equation now, which is here. I've taken the differential equation, initial condition. I have reduced the 4 and the 2. Oh, you know what? That would be 2. And then that would make this a 6. And then I also looked at this part and reduced the 2 there with that 2 and that 50. That would give us a 1 over 25 plus t, and then times the a. So let's decide how to solve this. It is a first order differential equation, which all of the problems we've been solving are first order. It's linear. It's not separable. Meaning the right-hand side, let's see, the right-hand side, we have dependent a, we have independent t, and we have multiple terms. We're not able to factor the right-hand side into a dependent expression times an independent expression. So it's not separable. We cannot use separability, not separation of variables. It's not separable. And so with linear, we're down to either integrating factor or muck. If you look at the coefficients on the dependent term. Here's a dependent derivative. If you look at the coefficient, it's 1. That's a constant. Here's the other dependent variable. If you look at its coefficient, not constant. So muck won't work. We're down to not muck. We're down to integrating factor. We need integrating factor. So let's do that. We would take the form. We need we need dA dt on the left plus the dependent linear term is equal to 6. For our integrating factor, let's use orange. Mu of t is e to the integral of the thing in front of the dependent variable. That's e to the natural log of 25 plus t. And we would get 25 plus t for our integrating factor. Then we take that integrating factor, 25t, multiply it on the right-hand side and multiply it on the left-hand side. The left-hand side is going to become the integrating factor times the dependent variable. The right side will be the integral of 6 with the integrating factor and dt. So let's integrate, let's integrate the right-hand side and then divide by 25 plus t. So 25 plus t times a on the left is equal to a 6 times, and then the antiderivative of 25 plus t is a 25t plus t squared over 2 plus a constant c, and we would have, let's rewrite, 25 plus t times a is equal to, if we distribute that 6 to the 25, distribute the 6 to the 25t, t squared over 2, and the constant. The constant we'll just rename as a new constant. So we have 25 times 6, what's that, 150t plus 3t squared. When you take the 6 and the 2, that gives us a 3, and that 3 there, and then the 6 times t, that's just going to give us a plus c, and now we need to divide by 25 plus t. So a is 150t plus 3t squared plus c, all divided by 25 plus t. There we go. But now we need to find our constant with the initial condition. So let's recover c with our initial condition, which was a of 0 is 2. And if we plug in that, let's take this, let's put it over here. And we're plugging in a of 0 is 2. So 2 is equal to 0 plus c all over 25, and c then is going to be 50. So when we rewrite our final solution, so the final solution, a of t, it's going to be 150t plus 3t squared plus 50 all over 25 plus t. There's our final solution. And just to go back real quick, that's our cat feeder for our cats, with Annie's voice recorded telling them to come eat. Right, so there was our tank, our initial value problem in, initial value problem in red, requiring our differential equation and our initial conditions. Initial condition. And let's do that. Then we looked at the volume. We looked at a domain. Here was the volume there. Here was a domain right there. Set the volume equal to a max capacity to figure out what time it would be full, or Similarly, what time it would empty, you'd set to 0. Here's our domain for the problem. Then we went to solve. We went through how to decide what to use, what method, and we decided on integrating factor. And then we moved through integrating factor, got a general solution with the missing parameter C, then came back with our initial condition, recovered the C there, 50, put it in there. Here's our explicit particular solution for A. Any questions? Please reach out. Y'all take care.